Thank you for watching Knowledge Academy. All right, today we are going to talk about center of mass and linear momentum. Okay, now let's talk about all these topics one by one. And my goal is to go over all the concept and then we can do problems relevant to them. So first thing is, what is the center of mass? Okay, so let's talk about here. Center of mass. So center of mass means it's very fairly simple. If you have a, let's suppose if you have a object like this, right? It's a rectangular or square shaped object. I can call it 1, and its mass is m1, and m1 equals to 10 kilogram. The question will be where this m1 will be acting. So usually what we do, if it's a normal shape, or it's a uniform shape, or a regular shape. Regular shape means it does not like an odd shape, like this shape is not a regular shape. If it's a regular shape, you can just make like a diagonals like this, and you can find this point, which is, you call it geometric center, right? So we can call this point a, the red color point is a geometric center. And we can also call this center as a center of mass. So now if you want to be drawing a diagram, like a free body diagram, usually you're going to be drawing like this. You can draw this point, you're going to draw this and call this is my W1 equals to M1G. Now, center of mass is going to be a challenge when things are not regular. For example, if I have a shape like this, now in this case, what I'm going to do, I'm going to be split. I'm going to be split, right? I'm going to be split by shape, and it's going to be splitting like this. And it's going to be, yeah. So now it becomes two regular shape. I can draw this guy here, this guy here. And I got this point, and I'm going to be doing same thing over here, same thing over there. I got this point. Now you can see these 2 points are a little bit out. They are not along x-axis, they are not along y-axis. I'm going to draw a line just in case. This line. Right? Now the case is that where is the mass is applying? One theory is that you can apply one mass here and one mass here. But since this is a one object, I should be applying only one mass somewhere along this line. Right? Somewhere along this line. I don't know where it's located. So let me draw this object again. And now I'm going to be drawing this object pretty much in this shape. Same object I'm going to be drawing here, and I need to define somewhere here there will be a point where I apply my total mass of this object. Right. Now the issue is that how can I get the coordinates of this mass? I want the coordinates of this object, center of mass. So what we do, the formula is that it's fairly simple. All you can do is I need the x component and I need the y component. So what you're going to do, you're going to be finding the x component of this one. I'm going to call this is object 1 and object 2. I combine them and making a common object. But let's suppose I can consider as a body 1, body 2. So body 1 have its mass. I can call x1 and y1 coordinate. This one have its own coordinate x2, y2 coordinate. Right. Now in this formula, how can I get this one? I'm going to be writing like this. My x component of my total mass equals to x1 m1 plus x2 m divided by m1 plus m2. So whatever, if there is, let's suppose they have a 3 object, you can add another one called, third portion of the body. And let me just draw here, for example, if I have a shape like this, uh, you know if I have a shape like this, what I'm going to do, I'm going to split maybe this way, and I can cut this one, this x1, y1. I got this x1, y1 for this point, and I got this x1, y1 for this point. Let me call x1, y1. Can call this one x2, y2, and this one may be x3, y3, and vice versa. If you have many, you can just do, you keep adding them. So you can adding dot dot dot, you can call x n m n divided by plus dot 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 x n. N means number of bodies or object. Same thing I'm going to be writing the y component, and it's going to be equal to plus m2 y2 plus dot 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 m n y n divided by m1 plus m2 plus dot 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 m n. Okay. You want to write another way, we just do it different ways, but this is pretty much the concept of center of mass, and you can be applying the center of mass concept in any object, right? Any shape. If let's suppose you have a shape like if you have a shape like probably I'm gonna say abnormal, like a potato shape. It's like a potato. If you want to find the mass of a potato, you cannot do that. So what one thing you can do, you take a line and then creating a bunch of lines like this. Depends on how much accuracy you need, right? And then you split it this way. Depends on how you're splitting. Size of these boxes can increase or decrease the accuracy, right? And you can go every box, like this box called M1, right? This box called M2, then M3, then M4, right? Same thing if you go and then you need to find out X1, Y1 for this box, this little box. Same thing for this one, you're gonna go to, sorry, X2, Y2 coordinate, then X3, Y3 coordinate. Same thing here, X4, Y4 coordinate. And then you can apply the same rule. What is my X component or combine, and Y, when I can just write here m1 x1 plus m2 x2 dot 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 whatever m component. Since I have a many component here, I don't want 4, 5, then 6, then 7, then 8. You're numbering them. I can call m n x divided by m1 plus m2 plus dot 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 m n. Same thing, I can write the y formula plus m2 y2 plus dot dot m n y n divided by m1 plus m2 plus dot 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 m n. Okay. Now let's go back and look into the other topics. We're going to be doing problem for this one. The other topic we have is Newton's second law of motion and the force on the particles. Newton's second law of motion and the force on the particle. So really, this is a very interesting phenomena on Newton's second law or in the force of the particle. It's you can say that if I have a component, right? If I have a particle component, and I can call this is object 1. And what is going on here in this component? This component is being, let's suppose, moving in this way, right? Moving in this way. So it has an acceleration this way. But this acceleration is not really along x-axis. It's not along y-axis. It has some angle, maybe an angle theta. So you're going to take this A, right? And this A, you're going to be just split into two. One is a AY, one is a AX. And you're going to be apply Newton's second law in each axis individually. So I'm going to be apply here and here on both axes. And I'm going to be apply here called f equals to max, since I'm applying along x-axis, and here I'm going to apply along y-axis, so I'm going to say is f equals to may. Now I can also say that this is fx and this is fy because these are two different forces. I can also write, I can combine the two. I can write my total net force on this particle should be equals to M A total. And this MA again is going to be equals to this. And let's suppose if you have another component, basically maybe third component is 3D, like 3D case, where you have acceleration, there's a y component, there's x component, there's a z component, and you want to split this component into one axis. So this is my AX, this is my AY, and this is my AC. In this case, my total acceleration will be equal to square root of ax squared plus ay squared plus az squared, and I can write maybe another form of here, writing here plus f z equals to m ay z, and I can also need to add a az component here, right? You can write like this. Yeah. Now the thing is, if I have a particle here, right, it's applying force this way and this way. I have two forces, F1 and F2. What I'm going to do, I need to apply the same rule, F equals to max, but here I don't have one force here, I have two forces. And both are in opposite directions. So what I'm going to do, I'm going to be split this force into this direction, split this force into this direction. Maybe I can call F1x. So I'm going to be writing here F1x, since this is a summation. Summation means the sum of all the forces or sum of everything. And I'm going to be writing here F1x, then minus F2, then minus F2, because the net force equals to max. And thus I'm going to be moving forward from there. Yeah. Same thing if I want to write in this is a 2D case, right? Two-dimensional case, which is most common. And if I want to be writing a Newton's second law of equation here along y-axis, since I don't have any force along y-axis except this force, so I have only one force, so I'm going to be writing F1y equals to MAY. And M is the mass of this object, right? That's what we use. Now we're going to be moving forward into a linear momentum, right? So talk about the linear momentum. First thing first, sometimes students are confused. What is a linear momentum? Or basically the first term come in your mind is, what is a momentum? The first thing comes in your mind, what is a momentum? The problem is that momentum is a derivative, right? Momentum is not a force, momentum is not a velocity, momentum is a product. So the formula for momentum is a product of mass times velocity. That's the momentum. Usually momentum is representing by P, so P equals to M times P. P is representing by momentum. We are talking about right now just a formula. The unit should be equals to kilogram meter per second, right? Kilogram meter per second. And if I want to be doing this thing, maybe I can just do one more thing. I can take kilogram meter per second. I can multiply second. I can divide it by second. I can do this, right? Divide it, multiply by second. So this whole thing, like this whole thing, can be represented by Newton. So really, I can write the unit of momentum units are, the first one unit should be kilogram meter per second. The other unit should be Newton second. Right? Newton second is the second kind of unit. So both unit can be used. Depends on which aspect you try to solve the problem. Let's talk about momentum and what is the definition of momentum. Right? So what is the momentum? Remember, momentum is not a single quantity, it's a product of two quantity, which is mass and velocity. So really momentum is, my definition is, momentum is a motion or is a quantity which is stored in a body in the form of motion. Momentum is the amount of motion stored in a body. And what does that mean? Let's take a look. You have a car, right? You have a car. Let's suppose the car is on the road, but it's parking on your driveway. Right? Stop. Velocity equals to 0. So if I calculate the momentum of this, it's going to be P equals to mv. The mass of the car is whatever, 2000 kilogram. Let's suppose heavy car, 2000 kilogram. I multiply that 2000 times 0, my P1 equals to 0. It means no motion. No motion car is, is parking in the driveway. So no motion. No motion means no momentum. And it means nothing is stored. Nothing is stored. Right? You sit in the car, you start moving the car, and car is getting speed higher and higher, right? So car is going to here, then car is going to here, and car is moving faster and faster. Here car velocity is, maybe velocity is 10 meter per second. Here car velocity is 50 meter per second, right? Now if I want to calculate the momentum here, P, I'm going to call 1 point, 2 point, 3 point. The point 2, I'm going to be calculating momentum. Momentum equals to mass times velocity. The mass is 2000 times the velocity here is 10. The answer would be 20,000 Newton second or kilogram meter per second. That's what we learned. I can use this unit or I can use that unit. But the number here is this. Number here is 20,000, right? Now let's calculate the momentum on point 3. So P3, I can call them P3 equals to 50 times 2000. The answer would be, right. And the unit would be kilogram meter per second, or you can call it per second. Either one of will be acceptable. Usually depends on which context you're talking about. So you're going to be using those units. Okay. Now, if you think about it, in a minute, car have no motion stored here. Car has some motion stored here, and then car have a lot of motion stored here. A lot. Right? It means if store means you can use it. But as soon as if you lift your foot out of the gas pedal, if you're driving your car at point 3 and you lift your foot out of the gas pedal, what's happened? Car is keep going on and on and on and on and slow, and then completely stop. If you lift your foot from here, it's gonna car go and then suddenly stop because have only few things stored. Here, no store means doesn't matter if you lift the foot, it's not gonna move anywhere because there is no motion there. So bottom line is then momentum is a motion stored in a body. Let's move on from this point. Momentum is already stored in the body. Let's suppose car is moving, momentum is already stored in this body. Now you can use this motion, you can store only, you can use the thing which is being stored. So I can use this momentum for its purpose. So let's move on to the other topic called collision impulse. Okay, is very relevant to the continuation. Okay, so the continuation of this, let's suppose you start your car is going here, then car is going here, car is going really fast here at 50 meters per second. So let me go to the next slide, right? And drawing a car here, drawing a car here real quick. This car, the car from previous slide, it was driving with 50 meters per second. The momentum we at 2000 kilogram car, the momentum we calculate is 100,000 kilogram Newton meter per second or Newton second. I'm just using both units, Newton second. Now, the first thing is collision, collision, and the second thing is impulse. So let's distribute this. What is collision? Collision is a event. Collision is event means two things are collide means impact. Impact is an event, right? You have like usually people have an accident. This is accident is a collision. Accident is a collision. So it's an event. I mean, it's not a science based event. It's basically an event. It's an event. It's an accident. It's called a scene. Right? You saw somebody have the accident. Right? You saw somebody have the accident, and that's a collision. So collision is right when two object. I'm going to write here. Collision means two object exchange momentum. Right? And what does that mean? It means I have any object here and I have another object here. Let's suppose this ball is stationary and this ball is rolling and hit this ball, boom, and then hit what's happening. This ball, number one, number one ball actually maybe keep roll and hit number two ball and maybe it slow down, number one ball slow down, but number two ball was not moving, it start moving. So what's happening? Some momentum from P1 exchange or transfer into P2. So P1, whatever is there, but P2 definitely 0, right? Because the ball was not moving, we already calculate. If it's not moving means the momentum should be 0. But after the collision, what's happening? This guy start moving, it means some momentum minus from this body and add in this body. Minus in this body, add in this body. That is called collision. Now, impulse is how fast the transfer happens. Impulse means really how fast or how large, right? How large the momentum transfer occurred during collision. How large or how fast the momentum transfer occurred during what? During collision, because collision is an event. Okay. So let's assume if this wall is here and you're putting maybe a chair on the road. You're putting a chair on the road. And maybe just draw the chair just in case, right? I have a chair that this road is going on and you're putting a chair on this road. And this chair sitting here, so the velocity of this chair is 0 and momentum of this chair is 0. But you coming, car is coming and hitting, and then what's happened, this chair is gonna boom fly in this location, right? When chair is moving, it means P no longer 0. It has some velocity, right? It has some velocity. So what's happened? Let's suppose I'm going to put some numbers just for this prospect. If let's suppose the momentum here was, I already calculated 800,000, momentum here is 0, and car is coming, and then hit this chair. As soon as they hit, what's happened? I can just make it maybe, a collision happen, right? Collision is an event, right? And collision means transfer of momentum. Now what's happened? This car have momentum for 100,000 kilogram meter per second. Now let's suppose after its collision, this car slow down and its momentum is reduced to maybe, you know, a 90,900, 90,900,000, right? Or maybe, it would put some uh, full number. So 100,000 now after the collision it is 99,000 kilogram meter per second. That's reduced. So how much reduced? I think the minus is 1,000 reduced. What's happened? This should be the when the chair is flying after this hit, right? This chair is flying. Their momentum should be the one used. So it should be 100. Oh, sorry, 1,000 Newton second or kilogram meter per second. And how fast you can calculate or how fast this momentum transfer, that is called impulse. So what is the impulse formula? Impulse formula is this, and that is impulse equals to force time, like how much force is, how hard you hit this chair and how much time it takes, right? How hard you hit this chair, this car is hitting, this is force, and how long it will in touch and after the chair is flying. So let's suppose, if you multiply that two, they should be equal to 1,000. So really impulse should be equals to delta P. How come I know? Because the momentum was 100,000. The momentum is reduced by 1,000. So I'm going to be writing this equation. This impulse equation is like this. It was 100,000 and minus, now it's now it's you know so what is the delta? Sorry, 99,000. And so what is the delta between the two is 1,000. So I can say impulse equals to 100, 1,000. And impulse formula is F times T. So they should be equals to 1,000. So I can write like this: F times T must be equals to M1 V1 minus M2 V2. See, these are the two momentum. I can write like this. So impulse, bottom line is that impulse can also be written change in momentum. Change in momentum. Right? That's another definition. Let's moving forward. Now we're going to be talking about conservation of momentum. And what is the conservation of momentum means? Conservation of momentum means, this is a topic we talk about, conservation of momentum. So conservation of momentum means you have the momentum of a system before and after collision must be unchanged. What does that mean? Must be unchanged means even though the two objects are exchanging, momentum. Let's suppose same example. There's a chair here, and there's a car is coming and hitting this chair, and this chair is flying. We talked about earlier, the chair momentum is 1,000. Now the car momentum is 99,000 now. But before the collision, the car momentum when car was here, somewhere here when car was here, the car momentum was 100,000, and the chair momentum when the chair was here, chair momentum initially was, I'm going to draw the chair maybe here, the yellow color means stationary, the chair momentum was 0. So I'm going to write in this, and then we can say how the conservation of momentum can be written. So earlier I have momentum of car, or I can call initial momentum of car, initial momentum of car plus initial momentum of chair must be equal to final momentum of car plus final momentum of chair. Let's substitute the number. Initially car was 100,000, the chair was 0. Now the car is 99,000 and the chair is 1,000. If you add them, both sides should be right. Both sides should be equal. So can I say that in another words, I can go and then say that initial momentum must be equal to final momentum. When for elastic system, initial momentum must be equal to final system. So maybe I can write m1 v1 plus m2 v2. I have two velocities must be equal to m1. Remember, even after the accident or even after the collision, mass doesn't change. Velocity change to v from v1 to u1 and v2 to u2. Some books are doing other way around. They call initial velocity u, final velocity v. Maybe you can call initial velocity u or final velocity v. Doesn't really matter. But both sides should be equal. And this whole thing called is called law of conservation of momentum. So in law of conservation of momentum, two things happen. Number one, momentum conserve for elastic system. We are talking about for elastic system. Momentum conserve. Number two, Ke, which is kinetic energy, also conserved. So how can I write the equation just like momentum for the kinetic energy? So this is momentum. I want to write the equation for kinetic energy for the system. So I'm going to be writing half m1 v1 squared plus half m2 v2 squared. Remember, half mv squared is a Ke formula. You can write here half 1 u1 squared plus half m2 u2 squared. And let's talk about real quick about momentum in one dimension or two dimension. Momentum into one dimension, two dimension. So let's do it real quick. So one dimension, I'm going to say is one dimension. And then here I have 2D or two dimension. You can also call this 1D, one dimension. What is one dimension is I have a ball is coming here, another ball is stationary here. This ball is moving this way. This ball is not moving. When they hit each other, you can write like this: m1 u1 plus m2 u2. So this is m1, this is m2. This is the velocity of this one is u1, and this velocity is pretty much u2 equals to 0 because they are not moving, or maybe they are moving. Doesn't really matter. You just take the number and plug into the formula. must be equal to m1 v1 plus m2 v2. I can also write the equation m1 v1 u1 square plus m2 u2 square equals to half m1 v1 square plus half m2 v2 square. So this is my momentum equation. This is my momentum equation, and this is my KE equation or kinetic energy equation. And this is pretty much law of conservation of momentum in one dimension, right? You don't add anything here. Maybe if you want to add, you can add x because it's along the x-axis. Everything along x-axis. Along x-axis could be x or could be y, one at a time. 1D means one at a time. Could be x-axis, could be y-axis. Two dimension is a little bit different. In two dimension, you're going to be writing or maybe looking into the problem. It's like have a ball is coming. Maybe this the other ball is not in the same direction. Maybe the other ball is right here, and this ball is going this way. Maybe this ball is not moving. Let's suppose this ball is not moving. Now this ball is moving, so the velocity is not along x-axis, not along y-axis. The velocity is along certain angle. So it has one component here, one component there. I'm going to call V, and I can call it U1x, U1y. Here, this ball is stationary, so the U2 is 0. But after it hitting, after this ball gonna hit, this ball may be also going there. So it also have a velocity of some of on the x direction, some of on the y direction. So I'm going to be writing the equation in x-axis and y-axis. So I'm going to be writing equation for momentum. Let me just draw a line here so we're not messed up. So for two-dimensional equation, I'm going to be writing un1 u1x plus m2 u2x equals to m1 v1x plus m2 v2x. This is along x-axis, and y-axis is going to be looking like this. u2y, and u2 is the y component of the velocity, and u1 is the x component of the velocity. So let's suppose u here, I can draw u here. This is u1. u1 have one component here, which is x component, and you have one component here, which is a y component. Same thing, I'm going to be writing complete this equation. u2y, sorry, this is u1y equals to m1 v1 y plus m2 v2y. Okay, I can write the same form of the kinetic energy equation. Since I have no space, I can just write it and then write and just putting x and y. All right, let's take some problem and see how does it go. All right, we're going to be doing some problem to understand these concepts a little bit better. All right, from here, let's read the problem. A 2 kilogram particle has xy coordinate of this one, and a 4 kilogram particle has a xy coordinate that one. Both lie on the horizontal plane. They are on the horizontal plane. At what x and y must be placed a 3 kilogram object such that the center of the mass of the 3 particle system would be like that much. So really this rephrase this problem again one more time. What exactly saying? Let's draw the diagram so we can understand better. Maybe I have one object here. I have a one object here. I can call maybe a 2 kilogram object, and I have a 4 kilogram object. The x component, y component for this one is given. X1 and y1 is given, and I can call this is object number one, right? This is object number one, this is object number two, and here the x1, x2, and y2 are given. Let me just write those numbers. It's going to be minus 1.2 comma 5 is given here. Sorry, 0.5, 0.5, and this one is 6.6 and minus 7.75, minus 0.75. Now they're asking if at what place you're going to be taking this yellow mass, which is, I don't know where is that, I'm going to be calling it number 3, and the mass weight is giving 3 kilogram. So where you're going to be putting this, where this whole system, I'm going to draw the system like this whole system. Right, so this one I do not have the x and y coordinate, so let me just make it just x3 and y3, x3 and y3. I don't know them yet. I don't know them yet. But in this question, they are asking you, where do you put this yellow mass in between the two, or maybe the side, wherever? I don't know where it's going to put. Where this whole system, red color arrow, I'm going to be drawing big arrow here. This arrow, this whole system, x and y could come out these values, minus 0.5 and minus 7 or minus 0.7. So these are the final. So these are my final coordinate of the whole system. So I will be solving this with just the formula I shown you earlier. X component equals to m1 plus x1 plus m2 x2 plus m3 then x3, and then m1 plus 2 plus m3. Here I'm going to substitute the values, and the values are like something look like this. 2, m1 is 2 values given, 2. What is x1? x1 is right here, minus 1.2 plus 4, and the x coordinate of the 4 is this 1.6 is given in the problem, plus 3, but third quantity is not given. I'm going to call it x3 maybe, divided by 2 plus 4 plus 3, and everything in kilogram, right? So I'm just writing kilogram for now. Here the x component is given, which is right here, so I'm going to be writing this 0.5 minus sign. Right. So if I'm going to solving, I'm going to be taking 0.5 minus sign times 2 plus 4, 6 plus 9, and I'm going to be writing this. You can multiply this, is going to be 2.2, 2.4, my bad. So minus 2.4, then plus this is going to be 6 and 2.4 plus 3x3, right? So I'm gonna see, I think I can minus subtract them, these ones, and I can take this one, so my x3 come from here will be minus 1.5 meter. Since everything is given in the meter, that's my answer. Right, I'm going to be apply the same strategy on y, and the formula will be m y component equals to m1 y1 plus m2 y2 plus m3 y3 divided by m1 plus m2 plus m3. If I do, then it's going to be look like I can multiply all these things, so it's going to be 2 times 0.5 plus 4 times minus 0.75, which is right here, and then plus 3 ny3 divided by 2 plus 4 plus 3. If I solve this one, my y3 come out to be minus 1.43 meter. So really you have to take this value, right? And then taking these values are the coordinates where you're going to be putting this 3 object into the middle of these two. In this problem, we have pretty much same kind of scenario. It's just like two object rather than a particle. This time, like I have a physical size of these object. So you can see here, and the d1 is right here. D1 is given that much, D2 is given 2.8, D2 is another parameter, and D2 is the depth. So really is a block like this. And the D3 is, which is the width of this, is given 13. So 11 centimeter, 2.8 centimeter, and 13 centimeter size is cube, consist of aluminum, right? And the half consists of the iron. So basically maybe this one is iron, this one is aluminum. So these two pieces, like same size pieces put together. Definitely iron is heavier, aluminum is lighter. So we want to find out where is the x and y coordinate of this and z coordinate. So we want x, y, z, all three coordinate into three different, you know, cases. So really I'm going to be drawing this, maybe look like this. I can just draw this object for a minute. So maybe it's like this. And I can split into this. I don't know where is the so one have this center is on the downward, this center also have a downward, but when you combine the two, that will be a challenge. I don't know where, maybe here somewhere. Maybe if you go down, it will be somewhere here. I need a coordinate of this point. That is my CG. CG means center of gravity. Some book they call CM. CM means center of mass. Progressing. Right? Because mass is applying where the gravity is, and where the gravity is, where the mass is. So I need actually three coordinate, and I'm going to be writing here. I need x, y, and z, and which one I can call maybe combine. Right? I can call combine or combine. Same thing with combine. Same thing with combine. Okay. Now the issue is that here mass are not given directly. Mass are not given directly. But we know one thing here is that mass is not given in this problem directly. So we know, but mass equals to another way, density times volume. Density times volume, or I can say mass equals to density times volume. That is something coming from physics mostly, and sometimes some students cover this topic in the chemistry subject. But anyway, we have masses not given directly, but mass can be calculated because density is given and volume is given for this object. The volume of one of if I want to calculate the volume, I'm going to multiply d1 times d3 and times d2, right? Length time width time height. So if I'm going to be taking this guy, taking this height, and only taking half of the block, because right, I'm going to multiply all three, I'm going to be getting the volume. So let me write directly the formula. The formula is d1, right? I'm going to be writing a By symmetry, the x component equals to d1 divided by 2. By symmetry, the x component, right, or x combined equals to d1 divided by 2, right? So really, if I take this whole thing from here to there, this somewhere in the center, I can go and that will be the center of first one. So it will be equals to minus 13 divided by 2. The answer will be minus 6.5 centimeter. B, the y coordinates, right? So the y coordinates of this one would be, we're going to be writing the whole formula. So y component equals to Mi means iron. I need the y combine of the iron and so I'm going to be writing iron plus M aluminum, mass of aluminum, and then y combine of aluminum. I can divide by both masses, so Mi plus Ma. And since masses are not given, I have to write off mass by this formula. So wherever the mass, I can write off with mass with density and volume. But density and volume go with material. So the density of iron is different than density of aluminum, as you can see in the problem. Vi and then y combine I plus rho A Va y combine A divided by rho I Vi plus rho A Va. Okay, everything I think here is given, just need to be substituted. So I'm going to be substituting here 11 divided by 2, right? 11 divided by 2 because half of this, and 7.85 gram per centimeter cube. I don't need to change the units because centimeter cube is also centimeter. So everything is given in centimeter. I don't have to do anything. Just leave it as is. Plus 3 times 11. Sorry, 3 times 11 divided by 2. Same thing here. In centimeter, and the density of aluminum is given 2.7 gram per centimeter cube divided by 7.85 gram per centimeter cube plus 2.7 gram per centimeter cube. Okay. If I solve this, everything will be answered. My answer should be come out to be y combined of these two will be equals to 8.3 centimeter. So I got first one is this, second one is this. Let's do the third part. C, I want the Z, right? But again by symmetry, because remember this block is symmetric in Z and X, so I can use the advantage. I can again by symmetry can say is we have Z combined equals to 2.8 centimeter divided by 2. So the answer is V combined equals to 1.4. Yeah. In this problem, we're going to be talking about momentum, right? Or linear momentum, mostly linear momentum. Now, since momentum can be one directional or it cannot be one directional, so we can split the momentum and call 2D momentum. So linear momentum, linear means is not changing its value throughout the duration. It's constant, but the direction could be one, or direction could be two. This case we have two-dimensional look like case. Here I'm going to be doing the given overhead, the path taken into be a ball of 0.165 kilogram, right? And the cue ball, so this is going to be cue ball is going here, bounces to the rail of the pool table. The ball initial velocity is 2 meters per second. So the ball is going here 2 meters per second. The mass is given is 0.165 in the problem, kilogram. 30 degrees angle, so 30 degrees angle, right? Theta is 30 degrees. So this one is also theta 2 is not probably given, right? But since this is a elastic momentum, so you can go and you can come at the same angle, right? Remember, this is not every time possible. If it's not inelastic, it's not possible. So this theta should be equal. So this is 30, so this one is also be 30 because of linear momentum, and it's also a elastic momentum. Reverse component of the ball, the velocity, but does not alter the x component. So really, the x component of this velocity and then x component of after the bounce is going to be constant, the same, not alter the x component. What would be the angle theta 2 and the change in the ball linear momentum in unit vector form? Okay, so we need to go through with this. Since I already answered the second part of that, of this angle, theta 2 should be 30, but I'm going to be writing some note here. So I'm going to writing A. Since the force of the impact of the ball in the y direction, Px is conserved, okay? Since the force of impact. So really what's happened there, the ball is going here and hit and come back, so it's going to be apply the force this way. So really anything happening in y-axis, nothing happened in x-axis, no force applied in x-axis. Or I can say that in x-axis, this direction or this force, whatever is there, or this, they're going to canceling out. So there is nothing happening in the x direction. So since the force of impact of the ball on the ball apply on the only in the y direction, since px means momentum along the x-axis is conserved, right? Conserve means not change, right? Conserve is not change. Maybe I can write like this here: px I initial momentum equals to px f, which is final momentum. We can also write like this: m1 v1x sine theta equals to m1 v1 sine theta 2 and theta 1, right? Here I think everything will be cancelling out. The only thing left over is theta 1 equals to theta 2. Theta 1 equals to theta 2. So with that, we already talked about that. This is a mathematical proof that theta 1 equals to 30 degree. We found theta 2 should be equals to 30 degree. The part B of this case, right, we need to find the change or momentum change. B, we need to find momentum change means P is a momentum change means delta. Delta means comes to the change. And this one is equals to initial momentum and final momentum. And initial momentum, these two are cancelled. So I don't really need to write initial the momentum along x-axis because they are equal. They could be, cancelling out each other. So I'm going to be writing m1 v1, and the momentum is only apply in. So I'm going to say this momentum this way. This is velocity. So there is one velocity component here, one velocity component here. I say this one is basically going to be not changed, so it's going to be conserved. So Vx component is not changing, so momentum is not changing along the x-axis, only y-axis is changing. So I'm going to be writing the y-axis. So if we m1 v1 cos theta 2, right, theta 2. So this is a component, and after hitting this is another component, right? So this is, I'm going to call v1, then v1, and then this is theta 2, and this is theta 1. So I'm going to be writing this and minus j, right? The j component is minus sign because negative direction towards that, then minus the initial momentum, and initial momentum is, so you can see here the momentum of this one is going to be this way. So p1y, the momentum of this one is going to be towards downward, so p2y, so it's going to be negative, this is going to be positive. So I'm going to be writing the final minus initial, so final will becomes with minus and initial should be coming with, and mass I don't have to write m1s because mass of this is not going to change, and I'm going to be writing cos theta 2, you can say theta 1 theta 2 both are same pretty much, and then j. If you substitute the value here, it's going to look like minus 2 velocity minus 0.165, this is a mass, times 2 meter per second cos 30 dt. Right? So really this minus sign is going to go outside, it's going to be minus here. Right? This minus sign is going to be going out. This looks like going to be minus here. So minus and minus going to be minus 2. Minus and both are term are pretty much same. The only thing is that both are minus. So minus times minus, when you add them together, the answer will be minus 2. And cos 30 is 30, and here will be a j. If I solve them, everything is going to be answer will be minus 0.572 kilogram meter per second. Look like this is a momentum, and that is what the momentum is. The change in momentum is also a momentum quantity, and the direction is j. So it means this change in momentum happened along this axis, the y-axis. That is my answer. In this example, a 91 kilogram man laying on a surface, negligible friction, shove a 60-gram stone away from himself, giving the speed of 44 meters per second. What is the speed of the man acquired as a result? So really what's happened? Let's draw the diagram, diagram is very important in these cases. A man have standing on the, and he has maybe a 4 kilogram stone. He want to throw this stone away with velocity of 60, the mass of this stone is different. The mass of the stone is 68 kilogram, 68 gram, and throwing that with 4 meter per second. That's the velocity. So what's happened? This man is also pushing back himself because there is no friction, right? Friction usually in real life we have a friction. That's why when we throw stuff we can move because we have a friction to hold us. But in this case, no friction is given in the problem right here. Negligible friction, so it's going to be moving. Let me write, the equation of momentum. So initially the man is not moving, the stone is not moving, right? So I'm going to be writing the initial system. So I'm going to say the momentum, initial momentum of the system. Must be equal to final momentum of the system. That's what we learned, law of conservation of momentum. Initial momentum is 0 plus 0 because man is not moving, the stone is not moving. The final momentum is ms Vs plus m n Vm. Ms means stone mass and Vs means stone velocity, Nm means mass of a person, and Vn means velocity of the person. Here I need to find out Vm, how fast the person is start, or this man is start. So I'm going to leave mm here. I'm going to take the other stuff on the other side, so it's going to be minus msEs divided by m. In this case, everything is given. I'm going to substitute the value 0. With minus sign 0.68. So it's a gram, so I need to convert it to kilogram because that's my MKS system. So what I'm going to do, I'm going to write here. You can write this, or you can write here 68 divided by 1000 to convert it to kilogram. So the answer would be 0.068 kg. So I'm going to be using that one, 0.068 kg, and the velocity is 4 meters per second divided by 91 kilogram is the weight of the person is given right here. So substitute all the values, the answer would be minus 3. And it's telling me this man is actually moving. The stone is going this way with 4 meters per second. The man is going this way with 3, very small, like 0.003 meter per second. You can imagine, stone is very small. Man is pretty big. So man only move very slow while stone is moving very fast. So stone is moving with 4 meters per second because that's how much exchange of the momentum, right? Just so you know, just a reminder, whatever the momentum this stone gain, right? This momentum gain, because stone is going to gain the momentum. Same thing, whatever the momentum this person lost. So gain and loss should be equal. That is a conservation of momentum. Let's do another problem. Okay. In this problem, let's take a look into the problem. What is given? A 5.2 kilogram or 5.2 gram bullet moving at a speed of 672 meter per second strike a 700 gram wooden block at rest. So the wooden block is not moving at rest on a frictionless surface. There is no friction in the surface. So there is a block, the bullet is coming and then poking into the block, and then block start moving. Right? That's the case. The bullet emerging and traveling to the same direction with the speed of this. It means after the bullet poking or merging into the block, it penetrates inside the block. So the both becomes one. So when bullet and block becomes one, they are only one velocity. What is the resulting speed of the block? We need to find the resulting speed of the block, which is kind of same with the bullet because both are emerging. And what is the speed of the bullet block center of mass? Right? We need to find out. So let's do it. We choose x-axis initial direction of motion and apply momentum. So we are saying everything like a bullet is here, it's coming this way, and then the block is coming, everything is along x-axis, along x-axis. So we choose x-axis along the initial direction of motion. And we need to apply momentum conservation in this direction. And how it's going to look like is m bullet vi must be equal to m bullet vi, right, plus m block then v2, right? So we have a v1 or vi. I'm gonna call v1 v2 is more appropriate in this case. Let's do v1, right? And initially the block was not moving, so even though I can write a further here m block and you know v1, the block v1, this becomes 0 because block was stationary, is not moving. So this thing I just does not include into this formula, so I'm just eliminating this. Here I have everything is given except this guy v2, so I'm going to be writing 55.2, then 672 equals to 5.2, and then the total mass is 428 plus 700, and then v. From here I can find the v2 equals to 1.81 meter per second. Part B is asking you what is the speed of the bullet block center of mass. So bullet block center of mass, so we need to calculate B case. It is consequences of the momentum conservation. Get the velocity of the center of the mass is unchanged by the collision. We choose to evaluate it before the collision, right? Right before the evaluation, the collision we evaluate. I mean, right before the collision when the bullet and block is not colliding. So I'm going to be writing V component equals to M bullet, then VI. And after the bullet hit block, the bullet and block becomes one. So I'm going to be writing here pretty much M bullet plus M block. Since I have a limited space, I can move this guy on the other side because I need the V component, um, the combined velocity. So what's happened is bullet coming. Let's do this. The bullet coming, and it's poking maybe here like this and stuck. It is stuck. So both are actually moving with the same velocity. So V comp is the combined velocity of these two. Right? So I'm going to erase this guy and bringing on the other side of the equal sign, so I can save some space. And it's going to be M bullet plus M block. If I substitute the value, is going to be 5.2672 divided by 5.2 and plus 700. If you combine everything and solve them, the answer will be 4.96 meter per second. And that is my answer for the velocity, where this guy actually moved 4.96 meter per second velocity. Thank you for watching Knowledge Academy. Please subscribe my channel.